All right, one of the tougher concepts of this chapter is to balance a chemical equation. So once you've recognized a chemical or a physical change for that matter, physical changes wouldn't need balanced, but once you recognize a chemical reaction specifically, you can realize that the number of atoms you start with has to be the number of atoms that you end with. This is all based on the law of conservation of mass, or of matter, that we talked about as early as week 2. So the law of conservation of mass says that you cannot create or destroy atoms. You can only transform them. That's exactly what happens in a chemical equation dealing with valence electrons. Obviously, this is something that kind of hides behind the scenes in a nuclear reaction where you can change matter into energy, but that's a separate chapter back in week 4. So as we look at this one, we see that we have methane, CH4, and what you notice very quickly is you have 4 hydrogen atoms here, and you have 2 times 2, there's 4 hydrogen atoms there. These large numbers, called coefficients, are the way to understand that multiple molecules are needed in order to accommodate those extra number of atoms needed in order to match. So notice we have 1 carbon over here, and we only have 1 carbon over here. So 1 matches 1 just fine. Because we had 4, we use this 2 out front to say 2 water molecules are needed. That 2 times 2 gives us a 4. At the same time, this 2 also gives us 2 times this imaginary 1 for oxygen. Then we realize that there are already 2 oxygens in carbon dioxide. 2 plus this 2 gives you 4. And notice 2 over here times 2 also gives you 4. So there's a little bit of back and forth, a little bit of practice to go, side to side. Just remember that big numbers, those coefficients that will eventually be called moles, those numbers are multiplied across the entire molecule, the entire version of their subscripts. And we'll get quite a bit of practice coming up. So if we look at this example here, we see H2 plus I2. So one thing that should stand out very quickly is that we have 2 hydrogens and 2 iodines, but only 1 of each. The reason that we only have 1 of each is because H only has 1 electron, I only had 7 electrons. There was no way to combine them into an H2I2 kind of example. Given that issue of Lewis dot structure and the octet rule, if we started with 2 hydrogen atoms, where did the other one go? If we start with 2 iodine atoms, where did the other one go? Well, on paper, it looks like they vanished. But in reality, what happens is we actually make 2 of those HI molecules, because that gives us 2 of the H's and 2 of the I's that we had all along, because these were both diatomic, as we saw in the other video. So it's kind of like a balancing act, no pun intended there. We have a balance of products before and reactants after, and we want those to be equal. And that's the idea behind most of this video and this portion of the chapter, getting used to this idea of making sure you start and end with the same number of atoms, the same amount of mass in the end. It could be possible that you go too far. If you think that there's 4 HIs created, that requires you to multiply 2 times 2 to give you 4 hydrogen atoms and 4 iodine atoms. Just know that if you go too far by accident, because that can happen, just reduce these coefficients to 1, 1, and a 2. It's no different than reducing subscripts when we're making compounds back in exam 2. Now on exam 4, we can reduce coefficients, if possible, to get to their lowest common multiple that we want. And that's the imaginary 1, and that 2. So watch out for duplicates, watch out for other things. One thing that students like to do a lot, and this is unfortunate, they like to do it because it's easier this way. They like to just combine H2 and I2 to make H2I2, because that makes logical sense. Oftentimes in chemistry, you may not think that logic ever kind of plays along because things are always weird, positives and negatives, and how they work, and how gaining and losing are always backwards. But remember, H atoms, hydrogen atoms, only have one electron. They can only share once. Iodine atoms only have 7 electrons each. They can only share once. So if you can only share once, H2I2, even though it sounds cool or sounds like it works perfectly, that can never happen, given the octet rule and how atoms really work in previous chapters. So don't create new chemistry. We still either have to use Lewis dot structures or have to do charge crossing if metals are involved. And this is just why chemistry is tougher than other subjects. We're using old material in kind of a new fashion. So, all right, here's a fresh equation, chemical change, because notice N2 and H2 have now combined into something different. You may wonder, why did we pick NH3? Well, again, we can go back to those same kinds of issues as before. Nitrogen, being in group 5, has 5 valence electrons. It's going to share 3 times. Hydrogen has 1 valence electron, and it shares only 1. So this is why we get NH3. You can actually cheat a little bit and use the oxidation states or charges that we start to see at the end of this exam in about 2 weeks. If you look at this X and Y kind of process from exam 1, it tends to work because hydrogen pretends to be a lot like a metal. If you look at their charges, this is a -3. For the nitride family, this is a +1. For group 1 metals, although hydrogen not being a metal, still has the same favorite charge. When we cross these charges, we also get this exact same formula of NH3. So it works in multiple ways, especially when dealing with hydrogen, to understand that NH3 is the answer, not N2H2, which can exist, but not in this circumstance here, not in introchem anyway. So what we want to do here is recognize, if we make a chart, look at the N's and the H's and see what happens. So as we looked at reactants, arrow, products, we see that we have 2 nitrogens, 2 hydrogens based on their subscripts. And then we only have 1 nitrogen and 3 hydrogens. So obviously that's a mismatch, and these need to be equal, and they're not. So what happens next is we cannot change the formulas. N2 is based on the diatomic gas molecule. You can't change it. H2 is based on the other diatomic molecule. You can't change it. NH3 is based on Lewis dot structure or cross-charging principles, and you can't change that either. All you can change is how many of each of those little bricks do you stack in order to get this side balanced with this side. Right now, you're probably a little bit heavy on the left side because nitrogens are heavier atoms, and there's only 1 on the right and 2 on the left. So if we want to fix that first, in order to change this 2 into a 1, we're going to have to multiply this by 2, because then we can get 2. So 2 times 1 means put a 2 in front over here. By putting a 2 there, it gives us 2 nitrogens that we needed over here to match. It also gives us 2 times 3, which is now 6. And 6 hydrogens is too many on that side. We need 6 on the other side. So if we go back and we say, well, if we have 3 times 2, that's also 6. And now 6 and 6 are equal, just like 2 and 2 are equal. In order to get this 3, we're going to have to put it in front. So what it now shows is nitrogen molecules react with 3 hydrogen molecules in order to produce 2 ammonia molecules. So this is a 1, 3, 2 kind of balanced equation. So if you count atoms, You notice that this 1, 3, 2 pattern, and 1's kind of redundant. They usually don't show it. But this gives us the equal number of atoms where there's 2 nitrogens on the reactants and the products, and there's 6 hydrogens on the reactants and the products in that balanced chemical equation. So let's try this one. This one's different from the previous. The previous was nitrogen and hydrogen combining. Here we have methane and oxygen kind of combining in a sense in 2 different products. The ability to see O2, CO2, and water together in this kind of sequence would be what we call a combustion reaction. So this is the burning of methane, which is how some power plants over landfills have been created to do. So let's use that kind of process of, let's just start in the beginning and see what we have. So here we have 1 carbon. So if we have 1 carbon there, we should have 1 carbon on the other side, and we do. So 1 and 1 is equal. So right now, for carbon atoms, we're perfectly balanced. If we go to our second atom, we see that there's 4. So if there's 4, notice we only have 2. How do we get 4? Well, we can't write H4O because H4O doesn't exist. Water exists. But what we can say is if we need 4, put a 2 out front. 2 times 2 is 4 hydrogen atoms that we need. But at the same time, it's also 2 times oxygen, which there's only 1. That gives us 2 of those. So we'll have to take that into consideration here in a minute. All that's left is oxygen. Right now we only have 2 to start with, but we have 2 here, and now we have this multiplied 2 over here. Together that makes 4 total oxygens. If we need 4 total oxygens, that's okay, because oxygen molecules come 2 atoms at a time. If we need 4 total atoms, we'll just do 2 times 2. That'll give us the 4 that matches. So it's nice to check your work. Again, we can make a chart. Sometimes making a chart after makes just as much sense as doing it, along the way. We have C's, H's, and O's. And we realize right now that we have 1 carbon, and in the end we have 1 carbon. So 1 equals 1 just fine. Hydrogens we have 4, but then we did 2 times 2 to get 4. So we have 4 from methane. We ended up with 4 by getting and creating 2 water molecules. We also see that with oxygen, we have 2 times 2. That gives us 4 oxygen atoms. We have 2 oxygen atoms here from carbon dioxide, but now we have 2 times the imaginary 1 to give us the other 2, and that makes a total of 4 for the products. And now we're completely balanced. So it's like saying if we have a balance, we have a carbon on each side, we have 4 H's on this side, we have 4 H's on that side, and then we have 4 O's, and we have 4 O's. And that's completely equal, completely balanced, and that's what we're after in this kind of concept. So it took 2 coefficients of 2. So this is a 1, 2, 1, 2 kind of reaction. 1 carbon, 4 H's, 4 H's, 4 O's, and then 4 total O's, although they do come from 3 different molecules. Let's try another big one. So here, a quick hint in order to make this a little bit easier. Notice the pieces haven't changed dramatically. What happens here from reactants, arrow products, is we have aluminums, we have sulfates, we have bariums, and we have nitrates. So the fact that sulfate stays sulfate and that nitrate stays nitrate don't make it harder than it needs to be. Keep these ions, and you can reverse their charges to see that this was a +3 and a -2, just like exam 2. This is a +2 and a -1. That's the issue with this balanced equation, is when they doubly replace each other, as the name of this kind of reaction will end up being in our next video. Notice the charges are different, so they're going to be mismatched before and after. So pay attention to those superscripts. They need to balance out because their number of atoms, their mass needs to balance out. So if we have 2 aluminums, because of nitrate's -1 charge, we only needed 1 aluminum. So we're going to have to take 2 times that 1 in order to get 2. If we have 3 sulfates, 3 sulfates is a disadvantage because over here we only have 1 sulfate. And that's because barium and sulfate had a perfect match of +2, -2 charges. So because barium and sulfate are already pre-made, you can't change the compound because it's already, charge balanced. If we want 3 sulfates, we're going to have to put a 3 out front. That'll give us 3 sulfates. Unfortunately, that'll also give us 3 bariums. So we can go back and fix this. Because of nitrates and barium's difference in charges, we had to cross charges there. We only had 1 barium. By putting a 3 out front, we get 3 bariums. Unfortunately, this does give us 3 times 2, which is 6 nitrates, but notice we already had 2 times 3, which was 6 nitrates. So by choosing the biggest and the scariest compound, the one that had a cross of both charges, we were able to balance all the way through and not have to erase and go backwards. If we wanted to check our work, notice we have 2 aluminums. And then in the products now we have 2 times 1, which was 2 aluminum ions. For sulfates, we had just 3. But because of barium's different charge, we now have 3 times 1, which is also 3. And so far, so good. We're equal, like we should be. Barium, we have 3. When we did 3 times 1, we got 3 total. And then on the other side, we have 3 times a different one, which was still 3 total. Those are equal. And then nitrate, we have 3 times 2, which was 6 nitrates. And then over here, we have 2 times this 3, which gives us 6 nitrates. And that 2 balances. So this is a, we can put imaginary 1 over there if you want, but a 1, 3, 2, 3 kind of equation. And that's balancing reactions in a nutshell. So it's a little bit of back and forth, but if you check your work using a chart, you'll know when you're finished and when you should keep going. Just remember that if you go too far, you can always reduce. So we'll come back in a separate video and tell you about different reactions that still need balanced, but just the different types of reactions that exist.